Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about rapidly iterating on appendages and getting feedback on the design using ProteusDS. In particular, we want to talk about exploring rudder sizes and how that might affect maneuvering performance. So for this project, we're going to use the generic frigate example and just kind of highlight like what you would do to quickly check these things and how fast it can take. Now, particularly what I want to do is focus on the rudder. So this is the default project rudder size. It's not necessarily like hyper optimized. It's just the way that it's configured, and it has pretty good performance with that. So when you're exploring this, the kind of rudder configuration, you might be sort of exploring generally the rudder area and things like that. And I want to highlight how you can really quickly go through this process of evaluation. So the first thing that you would want to do is say we didn't know what size we would want to use, and we just want to explore variations on the area. What you can do, so if you look in the project here, I already have a build ship kind of set up. Now, what you could do is add a file name prefix here and call it rudder2, for example, and go through and start editing the rudder size here. So what I've already done is I've shrunk down by 20% I kept the same span, but I shrunk down the chord at root and the chord at tip. And then as soon as you run this, it's going to create a new build ship file for you and save it in the project and use that. And it's going to make a file database for you to load into other applications. So I'm going to show, I've already done that, and I'm going to show you what that looks like. So to load up an existing one, and you know how to do this from looking at the other video on sensitivity studies. We'll go exit. I'm going to add existing data, build ship. I've got my rudder2 file here already. Now, the funny thing is, if you actually will run this, let's just double check the rudder size. I'm running it again so that I can look at the build ship size. So you can see we've got the same span, but we've got sort of 20% smaller chord at root and 20% smaller chord at tip, and that's going to make a 20% reduction in rudder area and lower control capacity. So the funny thing is, if we plot the ship, just eyeballing it, like it's kind of hard to tell that there's that much. Like maybe it seems a little bit reduced in area, but it's not always obvious. So you can have these relatively subtle changes that can have big performance on maneuvering of the system. So how do we see what it's going to do, and how do we rapidly iterate on that? Well, we use the application called Fremo. Fremo is the time domain simulation tool within the Shimo 3D toolset, and what I've got set up here, it's really basic, but I've got a maneuvering command with an initial RPM, 255 RPM, and then I've just maximized the rudder angle and we just run a little 100-second simulation. So the first thing we'll do is now that we've run build ship with our rudder2, you'll see this is the ship model file with rudder2 that's got the same name as we are using in build ship. So that's got our smaller rudder in it. Again, like we're not trying to make a smaller rudder, just kind of quickly, this is what you'll be doing to explore what the turning circle changes are like with different rudder configurations. So we'll save and run this. And of course, like the amount of time you need to run is going to depend on how big your ship is and how fast it's going and all that kind of stuff. But we can get really quick feedback here, and we'll look at plot trajectory. So you can see I've got the ship starting out here and it goes through a turn. You can kind of just eyeballing it here. We might want to make this a little bit bigger. You can see eyeballing it here, it sort of looks like it's a little bit more than 550 meters turning circle. All right, so this is where you would go back and adjust, make the rudder bigger. What does that do, right? So I happen to already have the basic file set up for the basic configuration for the generic frigate. So this one has 20% higher rudder area. It's the nominal configuration. And we just literally run the same thing again, and it just takes a second to run. Now we look at the trajectory here, and we get this rapid feedback from this nonlinear model of the turning circle and maneuvering performance. So you can see it's sort of about 450 meters. So we knocked 100 meters off the turning circle with that change in the rudder area. Fremo, of course, gives you other information that might be interesting. If you look at the displacement over time, for example, of course, you've got the global coordinates, position, and everything like that, but you get a dynamic roll angle as the thing is going through the turn. It looks like we have an initial roll angle here, so maybe let's set that to 0 and just see what the heel is as it's going through this dynamic turn. Plot displacement, and the roll goes as high as 5.4, and then it rolls back to almost 10 degrees and settles as it's going through that turning circle with a steady state angle at -8 degrees. So a little bit of an intense turn, but anyway, the idea here is that going through this calculation process is very rapid, and you can do these sensitivity studies, getting a really robust idea of what your ship turning performance is without necessarily, in early stage design, you can do this way ahead of doing any CFD and certainly any kind of tank testing, and really get sort of a confident idea of what kind of appendage size you would want to use. All right, that's it for now. Thanks for watching.